This unit of study deals with crop harvesting and storage. It will cover basic principles of harvesting and storing methods used for grain and forage crops. Much effort is used to successfully grow a crop to maturity. Much effort is also needed to properly harvest and store the product for maximum utilization. The proper procedures for harvesting and storage will depend on the type of product and its susceptibility to damage. Grain crops like maize, peanuts, and wheat, grown for food products or for next year's planting seed, are often harvested and stored more carefully than if grown for livestock feed. Hay crops, grown for their vegetative matter, are harvested and stored quite differently than crops grown for grain utilization. The next topic for study is the section on maturity concepts. You should now stop the VCR and study this section in your text. Then return to the VCR for further tutoring. Method and time of harvest are two major considerations for success in harvesting and storing crops. They depend upon the understanding of crop maturity concepts. Maturity classifications are most commonly described by the percent moisture of the harvestable product. Physiological maturity is the development stage where the desired product reaches maximum dry weight. The term can apply to the whole plant or only to the product of the plant, such as the grain. Although the moisture percentage can vary, most grain reaches physiological maturity at a moisture content somewhere near 40%. If damage to grain occurs before physiological maturity, yields and quality will probably be reduced. An example of damage would be early frost. Frost temperatures that prematurely ruin grain filling will result in smaller, shriveled seed that reduce yield and the suitability of grain for livestock feeding or human consumption. Harvest maturity is another maturity concept. On a practical basis, this is the stage of plant development that results in the best quantity and quality combination, depending on existing harvest machinery. Theoretically, you should harvest the seed right after physiological maturity is reached, since no more dry matter would be added to the seed itself. However, at physiological maturity, the seed is still at high moisture. High moisture seeds are more susceptible to injury and require greater drying costs for proper storage. On the other hand, waiting too long after physiological maturity can result in very dry seeds, which will easily crack or break during the harvesting operation. Yields can also be lowered because stalks may lodge, seed or ears may drop to the ground, or disease may infect the seeds during wet fall weather. Proper harvest maturity is also important in hay crop production. This depends on the relationship of yield and quality characteristics of the forage as it matures. It is important to note that as maximum yield of forages are reached, the quality of the forage in terms of digestibility, protein content, and amount of intake by animals decreases. This is true for most forage species. If harvest occurs at leafy or pre-flowering stages in grasses and legumes, quality is high, but forage yield is low. In addition, constantly harvesting forage too early will decrease stand longevity. Therefore, determining the optimum harvest time for forage crops is dependent on the individual producer's priorities in terms of yield, quality, and stand persistence. Most progressive hay growers attempt to maximize nutrient yields rather than total forage yields, and still maintain adequate stands for 3 to 5 years. For alfalfa, this is usually at the early bloom stage, the stage when flowers first begin to appear in the stand. Some farmers mistakenly wait for the highest yields that can be obtained on the first cutting, believing that total yields at the end of the season will be higher. However, delaying first harvest may actually decrease the total yield for the whole growing season. If the first growth is not clipped, the second growth from crown and axillary buds may not develop to their fullest extent, and the remainder of the growing season may be too short for 3 to 4 hay harvesting operations. The stage of maturity to harvest silage crops varies somewhat. If a grain crop is to be harvested for silage, the best time is usually when the grain is high in carbohydrates and the total plant is at a desirable moisture content for silage, usually 60 to 70% moisture. The stage of plant development for hay crops harvested for silage would be very similar to the best stage for cutting hay, that is, the best quality forage yield combination. Storage maturity usually refers to the moisture content of plant material that is optimum for maintaining high quality during storage. Most grains are not safe for storage unless the moisture is 14% or below. Many grains, such as corn, should be harvested at moisture contents much higher than 14%. But the grain must be artificially dried before storage. Harvest maturity varies over a wide moisture range and may actually overlap with the storage maturity range. A good example of this is soybeans. At physiological maturity, soybeans can be as high as 50 to 55% moisture. However, soybeans dry down rapidly in the field and can reach harvest maturity within 10 to 14 days after physiological maturity. Frequently, farmers delay harvesting until the moisture of the soybeans drops to below 13% to avoid drying the seed for proper storage. Proper storage maturity of forage crops also varies depending on how it is stored or used, and may differ from the harvest maturity. When forage is cut, the moisture content is probably 70 to 80%. To produce high-quality silage, the forage should be wilted to a moisture content of 60 to 70%. To produce hay, the forage should be dried to 25% moisture or lower before baling and storing. Thus, the harvest maturity is different from the storage maturity. The next topic for study is the section on harvesting and storing grain crops. You should now stop the VCR and study this section in your text. Then return to the VCR for further tutoring. Harvesting grain crops involves several steps. The plants are cut and gathered, seed is threshed and separated from the plants, and finally, the seed is cleaned. Harvesting by hand is labor-intensive and is still used in non-mechanized countries. The most common machine for harvesting grain in mechanized agriculture is the combine. The basic operations of cutting and gathering, threshing, separating, and cleaning are combined in one operation using the combine. Combines are used for harvesting almost all of the major grain crops. The combine shown here can be used for small stemmed crops, or those that are seeded in narrow rows or broadcasted in solid stands, such as rice, wheat, barley, oats, rye, sorghum, soybeans, and field beans. The same combine can be used for harvesting maize. However, the cutting and gathering unit in front of the combine must be replaced with a specially designed head that harvests individual rows of corn. Variations of the combine have been designed to harvest cotton and are commonly referred to as the cotton picker. Proper combine operation can result in an efficient harvest that minimizes grain loss and damage. Grain loss can occur at the gathering and cutting unit of the combine. Poor gathering unit adjustments, improper cutting height, improper ground and reel speeds, and dull cutting sickles can lower the amount of grain entering the combine. Grain that falls to the ground cannot be picked up by the gathering unit and lowers the harvestable yield. Rotating cylinders inside the combine thresh and remove grain from plants. This beating action, if too severe, can damage grain, which can be lost during the remaining separation and cleaning stages, or can reduce the market quality of the harvested grain. On the other hand, if the threshing action is not aggressive enough, grain will remain on the plants and be returned to the field at the rear of the combine, resulting in loss of harvestable yield. Seed is separated and cleaned from vegetative parts of the plants by shaking sieves and air generated by fans in the rear of the combine. Improper sieve and fan settings can result in incomplete separation and cleaning, resulting in grain loss from the rear of the combine. Effective combine operation is a must to realize maximum possible yields of high-quality grain. The rewards are readily evident in the filling and unloading of the grain hopper of the combine. Many farmers prefer to harvest grain as early as possible to maximize yield, improve product quality, and reduce field losses. To achieve these results, several methods have been used to facilitate grain harvest operations. Direct combining of standing crops is an easy, fast method of harvesting grain crops that dry down to harvest maturity and do not severely lodge before harvest operations. For crops that either lodge easily, prematurely drop their seed, are extremely weedy, or need additional curing time after cutting, windrowing may be used prior to combining. During windrowing, also called swathing, the crop is cut and placed in a windrow on top of the stubble. The windrowed crop is allowed to cure 2 to 3 days before combining. A combine equipped with a windrow pickup attachment is used to feed the grain into the combine. By windrowing and combining, the crop can be cut several days earlier than if direct combining. This two-step harvesting method reduces the possibility of field loss from premature seed droppage and lodging of plants. Grain in the windrow is naturally dried to a more uniform moisture content, reducing grain loss and damage. Furthermore, green vegetative material of the crop and weeds is allowed to dry, increasing the ease and efficiency of combining. Chemical desiccants and defoliants that are sprayed on the crop prior to harvest can be used to dry or remove the foliage. This practice is used, for example, to reduce green stains on cotton fibers during harvesting and to aid combine harvesting of alfalfa seed or extremely weedy fields. Different curing and storage systems also influence harvesting efficiency by influencing time of harvest. Storage of high moisture grain up to 25 to 30% moisture is possible using airtight storage to reduce spoilage. This storage method would allow earlier than normal harvesting time. Also, if drying facilities are available, crops could be harvested earlier and later dried to safe storage moisture levels. Proper grain storage practices are essential to preserve grain quality prior to utilization. Grain moisture and temperature are key factors which will determine whether quality of grain is lost during storage. Colder and drier grain drastically increase the allowable storage time without serious deterioration of the grain. When temperature and moisture of the grain are too high, disease and insect growth can occur, and the grain can respire at high rates. This results in lower feeding value either through loss of nutritional quality, producing toxic substances, or lowering the palatability to livestock. Several options can be used to prevent spoilage of grain during storage. Using airtight storage to provide anaerobic conditions prevents the growth of insects, mold, and spoilage organisms that rely on oxygen for growth. If non-airtight storage is used, Proper ventilation of the bin is helpful to cool the grain and remove excess moisture. In temperate climates, winter temperatures help preserve grain quality during storage if proper ventilation is obtained within the grain mass. Moisture condensation can occur when warm air within the grain mass moves upward and begins to cool near the outer surface. If not properly ventilated, this moisture condensation can accumulate, causing grain spoilage. In warmer climates or seasons, overall grain temperatures increase. Therefore, it becomes very important to maintain grain dryness. Proper ventilation is also important during this time. During warm months, grain temperature can be relatively cooler than outside air temperature. This temperature difference can cause air movement within the grain bin, possibly resulting in moisture condensation and grain spoilage. During summer, it is important to ventilate the grain on dry days. Ventilating the bin with outside air on humid days can unintentionally increase grain moisture. Even with proper procedures, long-term storage of grain under warm months becomes risky. Drying grain to safe moisture levels for storage is a widely used practice for many crops. For long-term storage of grain such as maize, sorghum, soybeans, and small grains, moisture content of approximately 14% or below is desirable. Although small grains and soybeans often reach this moisture level in the field at harvest time, artificial drying for these crops may be needed in some years. Maize is frequently harvested at high grain moisture contents and artificially dried to safe storage levels. The speed of drying grain is important to maintain grain quality and depends on the utilization intended for the grain. In general, hotter, faster drying can be used for grain for livestock feed. Slower drying and lower temperatures are needed on grain for planting seed and food products. The next topic for study is the section on harvesting and storing forages. You should now stop the VCR and study this section in your text. Then return to the VCR for further tutoring. Harvesting forages as hay is a widely popular method throughout the world and has been conducted for centuries. The basic steps in mechanized haymaking include mowing the green forage, allowing it to dry or cure in the field from the sun's energy, raking the hay into windrows, and packaging the dried hay into bales or stacks, called baling or stacking. Baling is the most popular method of mechanized haymaking. Balers, which package the hay into small bales of 16 to 35 kilograms, have been popular for many years. Now, large balers that produce bales up to 1,135 kilograms are widely used to avoid the hand labor of lifting and moving bales into and out of storage. To obtain the greatest quality and quantity of hay, forages should be cut at the proper time, rapidly cured, and removed from the field. In subhumid and humid production areas, rain often can interfere or ruin hay harvesting operations. Unexpected rain on cut and curing hay often reduces leaf content and hinders proper drying. The mower conditioner combines mowing and raking into one operation. Mower conditioners are used to reduce the field drying time for hay, to reduce hay loss, to avoid the possibility of rain-damaged hay, and to improve hay quality. The machine also conditions the forage by breaking and crushing stems. Conditioning forage material helps release plant moisture and shortens the time needed for field drying prior to baling. Field chopping is another method of harvesting forages. The field chopper cuts forage into small pieces which can be moved by air and blown into a trailing wagon. The field chopper can be used in several ways. When the forage is cut and field cured to hay moisture content and then chopped, It is called field-chopped hay. When the green forage is chopped directly in the field without delay and immediately fed to livestock, it is called green chop. The field chopper is also used to harvest forage in silage-making operations. In silage operations, the field chopper is also referred to as the silage chopper or silage cutter. In addition to hay, silage is another major method of harvesting and storing forage. Silage, also called ensilage, refers to forage crops which have been preserved through anaerobic fermentation. In other words, the fermentation process takes place in the absence of air. The forage is field chopped and taken directly to silos for unloading and storage. The fermentation process takes place over the next few weeks during initial storage. This whole process is commonly called silage making or ensiling. Ensiling is widely popular because it is completely mechanized. Little or no drying time is needed, so harvesting is less dependent on weather. And silage is usually higher in quality than forage stored as hay. Most forage crops can be harvested and stored as silage. Maize and grain sorghum are two crop species commonly ensiled. The process of silage fermentation includes several steps. Immediately after unloading the chopped forage into the silo, normal respiration of plant cells and aerobic bacteria deplete oxygen in the silo. This oxygen depletion period may take only 4 to 5 hours, and anaerobic conditions are then created. During the next 3 to 4 days under anaerobic conditions, the population of lactic acid-forming bacteria increases to several million per gram of forage. During the next 12 to 15 days, the lactic acid-forming bacteria convert glucose sugar to lactic acid. This conversion results in little loss of energy and nutritional value and imparts a pleasant fermentation odor to the forage material. As lactic acid is produced, the pH of the forage drops from about 5.5 to 6.5 in freshly cut forage to approximately 3.6 to 4.6 after fermentation is completed. The pH is now low enough to prevent spoilage organisms from growing, and the forage material is preserved. The preserved forage is now called silage. Spoiled or poor quality silage has unpleasant odors and is lower in nutritional quality. This reduces the palatability and usefulness to livestock. Low quality silage is usually the result of ineffective or incomplete fermentation. Cutting and storing forage at the correct moisture, tightly packing material into the silo, and chopping the material into fine pieces help reduce the oxygen content within the forage mass and improve the activity of lactic acid-forming bacteria. If forage material is too dry, packing operations to reduce oxygen content are less effective. In some cases, water is added to the chopped forage during packing to increase effectiveness. Other additives may be used to increase acidity of the material. For forage material that may have a low carbohydrate content, ground grains, molasses, or other sources high in starch or sugar content may be added as an extra energy source for the fermentation bacteria. Silage can be stored in different structures which vary in air tightness and can influence silage quality over time. Although costly, upright, airtight storage structures are effective in maintaining silage quality over a long period of time. These structures are particularly effective for low moisture silage, which is difficult to pack tightly. The airtight, long, and upright design minimizes the amount of silage exposed to air and oxygen. Non-airtight silos may include some upright silos, bunker silos with raised sidewalls, trench silos whose sidewalls are below ground, and stack silos that are stacked above ground. In these structures, plastic covers may be used to help keep silage exposure to oxygen at a minimum. Even under the best conditions, some outer layers of silage may be spoiled. However, if proper management is used, high-quality silage can be obtained in a variety of silos. Another major method of utilizing forages is through grazing. There are millions of hectares of grazing lands throughout the world. Grazing has important advantages. Forages can be utilized on land too steep for mechanized operations. Thus, meat production can occur on vast land areas unsuitable for cultivated crops. Animals can obtain green, succulent feed, and livestock are not confined to small areas, so diseases and sanitary conditions are not as stressful to animals. Grazing lands can be categorized into two major types: rangeland and pasture land. Rangelands, also called natural grasslands, utilize native plant species from the area. These native species are naturally adapted to the topography, soil, and environmental conditions of the area. The conditions are usually unsuitable for crop production or improved pasture species. There are vast areas of rangelands throughout the world on many different continents. In the U.S., much of the rangelands are located in the western states due to steep topography, limited moisture, or high elevation, all of which restrict the use of unadapted pasture species. Pasture land refers to land whose native species have been replaced by introduced species. Examples of this would be Kentucky bluegrass and smooth brome grass in northern states, and Bermuda grass and Bahia grass in southern states. The term pasture refers to a confined or fenced-in area that is used for grazing. Pasture lands can be subdivided into permanent, rotational, and supplemental pastures based on management practices. Permanent pastures are those seeded to perennial species or self-seeding annuals that are kept indefinitely for grazing. These pastures are not rotated with other crops and are left out of a crop rotation system. Rotational pastures are those on land that is rotated with other crops. Rotational pastures are usually used several years and then tilled and planted to other crops. Supplemental pastures are grown to supplement permanent or rotational pastures when conditions might limit normal pasture production, or when extra grazing material is needed. Supplemental pastures are usually temporary, frequently lasting only a year or part of a year. Annual pasture species are often used, such as winter rye, other small grains, and Sudan grass. Selection of pasture types, pasture species, location of pastures, weed control, and fertility practices are important aspects of pasture management to maximize pasture production. In addition to pasture management, proper grazing management is also needed. Grazing management refers to the management of the grazing animal and can greatly influence productivity and maintenance of the grazing ecosystem. If given free choice, livestock will selectively graze the most palatable species or plant parts. This could result in overgrazing and death of the most palatable species, increased pasture waste, and lead to undesirable changes in species diversity. Grazing management can be divided into different categories based on grazing intensity. Different grazing intensities can be achieved by adjusting the stocking rate, which is the number of animals in a given area for a given time. Zero grazing is a system where forage material is mechanically chopped and fed directly to animals in a feedlot. In effect, animals are not allowed to graze. This is called green chop and is used more frequently on rotational and supplemental pastures than on permanent pastures. Selective grazing by livestock is prevented, and forage utilization is maximized. However, it involves more mechanized harvest expense and requires time and labor in harvesting and transporting material to livestock on a daily basis. Rotational grazing, also called rotational stocking, is a system where pastures are subdivided into smaller units called paddocks. Livestock are moved from one paddock to the next as needed. Strip grazing is a more intense form of rotational grazing. The pasture is divided into narrow strips large enough to provide needed forage for 1 to several days before moving animals to a new ungrazed strip. Rotational grazing and the more intense strip grazing allow recurring periods of grazing and regrowth during the grazing season. This helps maintain longevity and productivity of the plant species. Production per acre is usually greater than with continuous grazing. Continuous grazing, also called continuous stocking, is a system which allows livestock unrestricted access to an area throughout the grazing season. This system is frequently used on permanent pasture lands and rangelands. The labor of moving animals and maintaining a supply of drinking water are minimized. However, problems of overgrazing, selective grazing, and low grazing productivity per hectare are common with this system. Another form of grazing management is deferred grazing, in which animals are not allowed to graze the pasture until late summer or fall months. Deferred grazing allows the plants to accumulate growth and is used to help extend the productive grazing season over long or unfavorable growing periods. These pastures are called stockpiled pastures. Grazing systems must consider the delicate balance of land resources, plant diversity, and animals. Well-managed grazing lands can be an integral part of a sustainable agricultural production system. This is the end of the chapter on crop harvesting and storage. You should now be ready to try the self-evaluation test at the end of the chapter in your text.